So welcome to the Ask Me Anything session with Professor Ethem Alpaydin. This is the event hosted by the Silicon Valley chapter, formerly called as the Santa Clara Valley chapter of the IEEE Computational Intelligence Society. My name is Vishnu Pendyala, and I am the chapter chair. This event is also co-hosted by 12 other organizational units of IEEE. I thank them all for publicizing this event among their members. So it is now my pleasure to introduce Professor Alpaydin. Professor Ethem Alpaydin received his Ph.D. from EPFL, Switzerland in 1990 and was a postdoc at ICSI Berkeley in 1991. He taught at Bogazici University from 1991 to 2019 and Özyeğin University from 2019 to 2026, both in Istanbul, Turkey. He was a Fulbright scholar in 1997. He had visiting researcher positions at MIT in 1994 and EDAP in Switzerland in 1998. He is a member of the Academia Europea and the Science Academy of Turkey. His book's Introduction to Machine Learning, it's in its fourth edition, or rather, in 2020, it was in its fourth edition. And it also has an extended edition in 2021. And his more recent book is Fundamentals of Probability and Statistics for Machine Learning. Both were published by the MIT Press. Between them, they were translated. The books were translated into Chinese, Croatian, Finnish, German, Japanese, Korean, and Russian. We are really fortunate about having Professor Alpaydin today with us. Professor Alpaydin, let's start with something many students are grappling with today. So many students begin directly with deep learning frameworks without a strong grounding in classical statistical methods. Do you believe this deep learning first approach is detrimental in the long term? And which foundational concepts do you think are most important and currently underemphasized?
Okay. I think just like in any engineering discipline and also in machine learning, it's very important that students have a good grasp of the underlying theory before they start working on any sort of project or implementation. And as for machine learning, I think the basic requirements are just usual mathematical courses, math courses that you take during the undergraduate. So you need to know calculus, both the single variable and the multivariable calculus. For example, in multivariable calculus, you learn concepts like the partial derivative, the gradient vector, etc., which are really important in gradient descent and backpropagation. You need to know linear algebra. And another important topic is probability and statistics, of course. So these are the sort of like the basic requirements I think any student should know really well before they start working on any sort of application, because once you get the theory, the rest is just implementation detail. And the students should also be able to write the basic computer programs before they learn PyTorch, for example. I think it's very important that, for example, whenever you have any sort of machine learning application, you need to be able to write down the model, define what the parameters are, define what the energy function is, and you should be able to derive the gradient descent update rules, for example, given the model, given the energy function, and you should be able to write down the code that implements those update equations. And once you move on to data sets that are larger or models that are more complex or energy functions that are more complex, then you, of course, you can use PyTorch to make your implementation faster, but it's just an implementation detail. You need PyTorch just to be able to make sure that you have an efficient implementation. But you as the person should be able to understand completely the underlying theory, the model, the parameters, the energy function, the update rules, etc. The reason for this is that, well, in any sort of engineering application, there are always unknowns, but whenever you're doing machine learning, there's already so much uncertainty about the data, for example. So you always need to minimize the uncertainty, and one way of minimizing the uncertainty is that you get a good grasp of the underlying theory. So that's why I think it's those things are very, very important. So somebody said that there is nothing more useful in practice than a good theory. So theory should always be number one. And then you move on to implementations, and to be able to get your implementations more efficient, then you use PyTorch. Because if you do not have a good grasp of the theory, you will not be able to understand, for example, what's the role of the hyperparameters, like what's the role of a learning factor or the number of layers or whatever. So then it will be just trial and error. You have a PyTorch, you have a code, and you keep on manipulating the hyperparameters, hoping that there's going to be some sort of a useful result. So that's not going to be very fruitful, I think.
Yeah, I fully agree. In fact, that's what I tell my students as well. And by the way, most of the questions that I'm asking you today are from my students. I slightly reworded them and rephrased them, but most of them are from my students. So that was quite insightful and helpful to my students as well. So staying on education, I'd love to bring in your latest work. So let us talk about your recent book, the one published on December 2nd, 2025 by the MIT Press. It is titled Fundamentals of Probability and Statistics for Machine Learning. So most curricula today teach probability and statistics as prerequisites to machine learning. So how does your integrated learn by doing approach reshape the way beginners conceptualize uncertainty, inference, and model building from day one? And what might this mean for the future of data science education?
Okay, so yeah, that's a very good question. So what I feel myself, but that's my experience and also observe it in my students, is that normally probability and statistics is a course you take as a part of your undergraduate degree. But when you're taking that course, you're not really that much aware of the possible applications. For example, typically when people teach probability and statistics, for example, when you're learning probability, you talk about tossing coins, or you're drawing cards from a deck, or you're drawing, I don't know, colored balls from a bag, etc. But actually, the probability has a lot of real-world applications. And one of the important real-world applications of probability and statistics is data science. So I think that combining probability and statistics in a data science curriculum is very useful because of two reasons. One is that the students will be immediately aware of the real-world applications of probability and statistics. So it's not gambling. So you already need probability, and you also need probability and statistics in real life. So you're not tossing a coins, but when you think about the probability that a customer buys milk this week, for example, that's also something like a coin toss, or whether a patient has cancer or not. That's another type of coin toss. So when you talk about the real world applications, the students are more interested because it just connects the theory that they see in the course with real life. So they're better motivated. Another thing that's important is that normally when you take a course on probability statistics, there may not be that much of a programming support. So most of the time, those courses are taught by someone from the math department, and they're just completely theoretical. Whereas if you teach them in a data science context, you can also teach, or you can also see programming examples. So the students can also learn, for example, how to sample from a probability distribution, how to write statistical estimators, how to train them on data, etc. So it just makes the connection from probability and statistics to machine learning. So that's why I think this book is interesting, because in the usual approach, so a student takes a probability and statistics course, learns the basic concepts, and learns maybe also statistics, maybe learns linear regression, and then stops there. And then years later, you take a course on machine learning. This time you start from linear regression, and then. So I think that the good idea is to connect them in the same course, or sort of connect them seamlessly, so that because there's a natural transition from probability and basic concepts of statistics to machine learning. So if you divide them into different courses or different textbooks or different notations, etc., it becomes very complicated to understand. But if you teach them in the same course, you start from the basic concepts of probability, you move on to basic concepts of statistics, like you talk about parameter estimation, etc., hypothesis testing, then you teach linear regression, and then you can very easily continue, for example, with classification, or you can talk about neural networks, because it's just a nonlinear type of regression. So I think that's the advantage, is that, well, there are two advantages. That one is you seamlessly combine those two topics, because actually they are two facets of the same problem. And the second thing is that because it's related to data science, you can talk about real-world applications, and you can talk about programming exercises or programming projects. So I think that's why I think this book and this approach is useful. I think a similar sort of motivation can also be done for linear algebra. Because, for example, let's say the student in an undergraduate curriculum takes a course on linear algebra, but that course may be taught by someone from the math department. It's completely theoretical. But if you connect it with data science, then you can sort of also talk about different applications of linear algebra, and then you can include programming exercises, and then you can talk about real-world applications of linear algebra. So I think that's sort of what we're moving towards in the data science curriculum, as opposed to so in data science, though, we're sort of combining the theory and application, or the mathematical theory and the engineering applications. So that's why these data science curriculums, I think, are interesting. It's not just theory; it's theory plus application.
Yeah, speaking of which, and building on that foundation, so which problem settings do you believe these approaches, like the ones that you emphasize in your writing, like probability reasoning, probabilistic reasoning, Bayesian decision theory, or graphical models? So where do these continue to offer clear advantages over end-to-end deep learning, particularly in scenarios involving limited data, distribution shift, or interpretability requirements?
Right. Yeah, that's another very good question. So I think that there's sort of like two directions, or maybe two ends of a spectrum. Is that deep learning, so the interesting thing about deep learning is that you do not need to know anything about the underlying application. So the idea in deep learning, or why they are so powerful, is that you just build a neural network, a large enough neural network, and you have a lot of data, and you just feed the raw input, and it's able to generate the raw output at the very end. And you do not need to worry that much about what should be the transformation in between. So it's not completely agnostic. You do not need to know anything about the application. Assuming that you have a flexible enough model, and assuming that you have a large enough data set, the model will somehow learn to map the inputs to the correct outputs. So that's good. But that's only possible if you, as you said, it's only possible if you have a very, very large data set. But of course, the largeness of the data set depends on the application. But that's sort of the interesting bit about deep learning, is that you do not need to know anything about the underlying application. It's just assuming that you have a large enough data set, the model can learn automatically to map the inputs to the correct outputs. Now, the problem is that if you do not have a lot of data, you should add some sort of prior knowledge to your learning model. And that's where all the models that you cited become important. So those are ways in which you can incorporate your prior knowledge about the application to the learning model. So you're just manually introducing some structure. So it's not just like layers of neurons anymore, but you're somehow adding your prior knowledge to the network. For example, if you're doing image recognition, you know that if your input is an image, you know that nearby pixels are correlated. So in that case, it makes more sense to use convolutional layers early on, because you know that at the input level, at the image level, the basic correlations are between pixels. So that's why convolutional layers are important there. So as long as you have some information about the application, you're free to use that in defining your model. But of course, there's always a risk, because whatever you believe to be true about the application is not necessarily true. So it may be an advantage, but it may also be risky. So the idea is we call this the bias-variance dilemma. So it's a good idea to make your models as flexible as possible if you do not have a clear idea about what the underlying model is. So in that case, you should be like as agnostic as possible. Assume as little as possible about the underlying data. Use a model that's as general as possible. So use a deep layer neural network with many layers, with many units, and hope that the learning algorithm will be able to convert that data into some sort of a useful knowledge embedded in the connections of the neural networks. But if you do not have a large enough data, or if you have very strong beliefs, very strong correct beliefs about the regularities that underlie your problem, you can include that information, you can incorporate that information into your learning process. And you can do it in different ways, where you can do it by structuring your neural network, for example, having convolutional layers. Or you can do it by changing the error function. For example, you can, well, normally what you do is that we have an error function. In the ideal case, the only term in your error function is the error on the data. But what you can do is that you can add, so this is done, for example, in regularization, to your basic error function, to your basic data error, you can add additional terms which penalize things that you do not want to see. For example, that's what we do in L2 regularization, right? So you have the data, plus you want to penalize large weights. So you can do L1, L2 regularization. So that's another way of incorporating prior knowledge. Or you can think about different ways of pre-processing the data. So before you feed the data to your neural network, if you know that certain features are more useful, or certain pre-processing are going to be more useful. Or you can incorporate, for example, if you know that there are kernel functions or distance measures that are really useful, then you can try to incorporate them into the neural network. So that's sort of like the spectrum. You can choose to be completely agnostic, so leave everything to the neural network, so you just feed the data. Or you can help the machine learning system as much as possible by either modifying the network architecture, by modifying the inputs or the input representation, or by modifying the error function. So ideally, of course, ideally, it's best not to include any sort of prior information to the process, because there's always a risk that your prior beliefs may not hold, so that may be actually detrimental to the process. But unfortunately, if you do not have a lot of data in your data set, if you do not have a lot of training examples, you need to come up with some sort of simplifying assumptions, so that you can have a model that can be trained with limited data.
Yeah,
so that's what we call the bias-variance dilemma in machine learning.
Yeah.
Sorry to interrupt, but I have exactly a follow-on question, which just goes to what Dr. Alpaydin just discussed, if I'm allowed to.
Sure, go ahead.
So, more about the customizations to the model you mentioned. Actually, can you talk more about a use case where, like, we're trying to detect a rare cancer, like we're trying to train a model on a very rare cancer. So the data set is just really limited. And in such cases, what we did is we basically tried to get a 3D structure of the lumps that cancer forms in an X-ray domain, which is mostly like a black and white image. So in such cases, if we try to train a large model on this limited data set, then it doesn't do anything. So can you talk more about like what kind of customizations can one possibly do or things like that in such specific case where the data set is just black and white type of images and that too are very limited?
Well, I'm not an expert on medical diagnosis, and I don't know your particular application, so I can only talk on general
It's
terms.
basically about like YOLO type detection or maybe like MobileNet SSD type detection. But you know, as we were saying, like it requires different layers of convolution and stuff. So we were sort of trying to investigate into that type of thing, that
Okay.
how can we modify the model to make it better? And I
Yeah,
was trying to
indeed.
find some theory and stuff.
Okay, I think what people do frequently in image recognition applications when they do not have a lot of data is use some sort of transfer learning. So are you familiar with the idea of transfer learning? So
Correct. But
something like
since cancer itself is like rare, there isn't, you know, like existing model
no,
or
I
anything
know
like
that.
that.
Yeah, you cannot actually predict the cancer maybe from the original image, but you can use some sort of transfer learning. For example, copy some layers from a neural network that's trained on, I don't know, maybe similar image data, maybe not containing cancer, but using the same type of input. And then assume that maybe, for example, for that type of application, you have a large enough data set. So you actually train a network on that other application, which uses a similar type of input representation. And then what you can do is that you can copy some of the early layers of that network to your application. So assuming that whatever type of features that are detected for that application will also be useful in providing you a good representation for your application. Then what you can do is that using your small data, you can just train the outputs, the layers from the output of features, from the output of those features to your classes. Does this make sense?
Yes, sir, it does.
So that's the so that's sort of what I can recommend. For
Yeah,
example,
that's helpful.
let's say that you want to do, let me give you an example. So let's say that you want to do face recognition and you do not have a lot of face data, right? So what you can do is that, for example, let's say you take an large database like the ImageNet database and train some sort of a classifier on the ImageNet database. And then what you can do is that once you train that large network, you can take, I don't know, first 2, 3 convolution layers of your neural network trained on the ImageNet, and then use them as your layers in a face recognition data set. And there you're assuming that whatever type of features that are good for on the ImageNet database will also be useful for recognizing faces. So that's a very strong assumption, right? But if you can do this, so what you can do is that with your face data, you're only going to be training the layers from the output of those features to your classes. So you have a smaller, so you're just copying a portion of the network from another source. So that's the sort of thing that I can recommend. I don't know if it applies to your application.
Yes, it makes sense. And actually, we did some sort of like transfer learning, but it turns out that after like few layers, in fact, the performance was decreasing. So
So does this mean that it helps or it doesn't help?
it didn't help too much
It didn't
in
help.
case of transfer learning. So we also did some experimentation where we froze
Yeah,
different
yeah,
number of layers
I
and all.
think I think it depends on the application and it depends on how similar are those two applications, right? So you're assuming that whatever features that you detect for application A will also be useful for application B. So yeah, of course, there's not a guarantee, but that's probably the
Makes sense.
another way is the things that I mentioned before is maybe think about some sort of pre-processing the data, or think about maybe some sort of geometric features that you can extract from the data, maybe find blobs, like calculate their widths, height. I don't know the application, but try to extract some sort of high-level information from the input image. So that may be an additional source. For example, in face recognition, but typically what you do is you give your input is something like the image, right? So it's a 2D image. But another type of representation that was popular actually in the old times was, for example, you take the face image and you find, for example, the position of the eyes, and then you define new features like the distance between the eyes, the distance between the, I don't know, the eye and the nose, or the size of the whole head, the width of the head, the height of the head, etc. And so that gives you another representation. And maybe you can think about, I don't know if it applies to your application, but that may give you an additional type of feature which you may feed to your neural network. So if you do not have a lot of images, it may be very difficult for the neural network to extract the features, any sort of high-level features from the basic image. But if you can sort of do that extraction yourself, that may help you maybe with with classification. Does it make sense?
Yes, sir. It does make sense. Thank you for the thank you for your suggestion.
Taking questions from audience. Before we switch on to your research, Daniel Peters has his hand raised. So Daniel, can you please go ahead?
Dr. Alpaydin, can you hear me?
Sure, yeah, I can. Go ahead.
Thank you very much for taking the time for the AMA. Question for you. Let me give a little bit of history. In the late 1600s, the atomic theory was unknown, but steam engines were in use. And of course, without being able to understand really the chemistry and the physics of heat, they were experimenting to get to achieve better efficiencies. I feel we're in the same place today, because what you said before regarding having a powerful theory is critical to being able to make good predictions and analysis. We need that theory. I understand completely that we have all sorts of mathematical operations and statistical processes that mechanically we use in our artificial intelligence today, but there is no bridge to predict the rise of what we understand, or what fools us into thinking there's intelligence there. When will that theory, what is required to create that theory? Who's going to do it? Is it you? Possibly. Or somebody will have to come up with it so we can make more engineered decisions on our designs of AI process hardware. Where do we go from here to get to that point where we can make predictions? We don't have to guess, which is what we're doing now in deep learning models, dimensionalities, to come up with working solutions that may in fact fail at critical periods because we don't understand the theory.
I'm sorry, I'm not sure that I understand. Are you asking me what's going to be the future of deep learning, or?
No, let me more focus then. We need that theory. You mentioned at the very beginning of the MA that it's very useful to have a strong, accurate theory for the operation to make engineering decisions. We don't have that theory, and to my mind, we don't have that theory for deep learning models. Am I incorrect?
Maybe, but it may not be, but we do not have it completely, but we have some of it, and we're working on it. So I think the point that I'm trying to make is that I'm not saying that the practicing is useless or unnecessary or whatever. I'm just saying that the practicing or the experimentation should go hand in hand with theory. So let me continue with your example with steam engines. So you take a person like Watt, right? James Watt. So he was an engineer. He wasn't a theoretician, but as far as I remember, he had connections in Cambridge University. So he was in good contact. He was in contact with the theoreticians. So it cannot be just a blind sort of trial and error or tinkering with the machinery, hoping that somehow you can get the ideal model. But the two should go hand in hand. So you try things, you get some results, and then you try to understand why you get good results, or you try to understand why you get bad results. And then you get some sort of a theory, and then you test those theories by doing more experimentation, etc. So, and you're right in saying that the theoretical understanding sometimes comes much later. Let me give you another example from the history of science. So let's talk about the astronomy. So you know that in the old times, in the Middle Ages, people thought that the sun circled around the Earth, so all the planets circled around the Earth. So that was the Ptolemaic theory. And then Copernicus came up and said that, well, actually, it's the Earth that revolves around the sun. But so Copernicus was right in that case, but he was not completely right. But because Copernicus assumed that the orbits were circular and that the planets orbited in constant speed. So that's why Copernicus' model actually was not really very good. It was only with Johannes Kepler, who just looking at the data understood that the orbits should be elliptical and that the speeds are not constant. So Kepler had no idea why the orbits should be elliptical or why the speeds should be varying. So it was just the data analysis, just looking at the data that was collected by his former colleague Tycho Brahe, who made a lot of experimentation, who made a lot of observations, collected very, very large data sets. And what Kepler did was just data analysis, just trying to fit a model to the data. And the way you can fit a model to the data is that you need that the orbits should be elliptical and the speed should be varying. And that made a very good fit to the model, but nobody knew why. And it was only afterwards with Newton, who came up with laws of gravity, laws of attraction, etc., then we understood, or humanity understood, why it makes sense that the orbits are elliptical, or why the speeds vary, for example, when the planets orbit around the sun. So you're right in saying that we need to collect data so we can fit some models to the data. But at the same time, there should be this parallel search or parallel attempt to be able to extract some high-level information from that data. So the two go parallel, hand in hand. Yeah.
So
Does it make sense? Does it help?
Oh, absolutely makes perfect sense. So the question then becomes, how can we? It's hard to chart, since we're blind to the actual theory, how to find the theory that allows us to make to resolve this problem.
Well, people are actually, there's a lot of people working on the theory of machine learning. So there's a lot of people who are trying to understand what it is that we're, for example, about the convergence of these neural network algorithms. So what's really happening when a neural network learns, or what type of neural network structures match well with different applications. So people came up, for example, with models like transformers, the attention layers, etc., that match very well to certain applications. So there's a lot of people who are working on that. Yeah.
Okay, thank you.
Sure.
Okay, there's one more question on the chat. Christine is asking, she's saying that she was speaking to a group of students who were doing exactly what Professor Alpaydin, you said. They were basically changing hyperparameters in their code by trial and error. So their challenge with the math is that it is very abstract when it is taught, and they are more visual learners. So what advice would you have for teachers or students to help with this? How do we cope with the abstractness?
Well, I think the abstractedness comes with the, I think it comes a little bit with more theory and more experimentation. But I agree that it's not always straightforward to see the relationship between hyperparameter values and the underlying models, because, well, there's also a lot of uncertainty related to the data. So for example, you can have one neural network, one set of hyperparameters that work wonderfully on data set, and then you double the size of the data set, and suddenly those hyperparameters do not work well anymore. So there needs to be some sort of trial and error because the underlying data is random. But it should be maybe a little bit more maybe methodical, or needs maybe better designed experiments. So do not do something like a depth first search, change this hyperparameter, then this other hyperparameter, then this other hyperparameter, but do something like a grid search. So that's what's called factorial design in design of experiments. So these are the hyperparameters that I'm going to investigate. These are the different levels. And then in that search space, now I'm going to try a lot of configurations, and then I'm going to try to find the best model.
So I can probably add a little bit to it. So to address the abstractness of mathematics, in my classes, what I do is I use a lot of analogies. I ground them to the real world situations to help them understand and relate better to the abstractness.
Yeah. Well, if you, so once you have some knowledge about the application and also about the mathematics, you get a lot of intuition. For example, one of the things, for example, let's say you're doing steepest descent, right? And you see that there's oscillation, so it's not a very nice convergence. And then what you can do is that, for example, you might remember your course on multivariable calculus. So you remember in multivariable calculus, so when you think about the error function, so the shape of the error function is defined by the Hessian matrix, right? So by the matrix of second derivatives, second partial derivatives. And you know that, for example, the shape of that Hessian matrix actually gives you a lot of information about the shape of the optimized function. So we know, for example, if the contours of that quadratic surface look more like circular, then you can have faster convergence with gradient descent. But if the Hessian matrix is not well conditioned, then gradient descent will oscillate a lot, right? And for example, in optimization theory, there are techniques for changing the shape of, or I think it was called preconditioning or conditioning the problem so that you can, for example, get a better Hessian matrix that will allow you to converge faster. So if you know these type of things, that may help you in getting a better convergence, for example.
Yeah, thanks for that insight.
Yeah.
So before we take more questions from the audience, I want to shift focus to your research contributions. So in your 2020 paper, Continuously Constructive Deep Neural Networks, you propose a model that grows its architecture during training rather than fixing it in advance. So in practice, how do you determine when to stop adding capacity? And additionally, do you view dynamic architecture growth as a more principled alternative to neural architecture search or a fixed design space?
Yes. That type of algorithms, actually, I've started working on them when I was a PhD student in Switzerland. So one of the methods that I proposed in my PhD thesis, so this was in 1990, so that was an algorithm that I called grow and learn. So it was an algorithm, a neural network that grew when it learned, when it needed to learn. So it's sort of the same idea, is that you start from a simple network, and then once you understand that your current capacity is not enough to learn new examples, you need to increase the complexity. So that's done explicitly, actually, for example, by adding new units or by adding new units. And we talked about, I think, 2 different approaches for construction in that paper. But that's also sort of implicitly done also with a deep neural network. So you remember, for example, let's say you have a deep neural network with a lot of layers, with a lot of connections. So in the beginning, most of the time, we start with weights that are very close to 0, right? So if you have a lot of weights that are close to 0, so this means that actually you start from a very simple neural network, because if most of the weights are close to zero, it's as if those weights do not exist, right? So when you train your model, those weights start to move away from zero. And as they are moved away from zero, it's like you're dynamically increasing the complexity of your neural network. So it's actually the basic idea. It's either you do it explicitly by adding neuron yourself, or the neural network gradient descent internally moves weights away from zero and then effectively adding more parameters to the model. So it's just like, so there's not much difference. But I think the explicit thing sort of makes more sense in an engineering context because, but if you know that there are certain neurons that are not really doing anything useful, you do not need to waste any energy, for example, or any computation for them. And that's why, for example, people have recently understood that, well, you do not really need very large language models. You can actually do things also with a simpler model. So this just indicates that maybe most of the weights in a very large neural network are not actually, or most of the units in a very large neural network, they are not maybe actually doing something really useful. Maybe they're just weights that are there to balance some other weights, but maybe they're not useful. So that's why I think this constructive idea is interesting in the sense that you start from a small network, or you start with a small model, and then if you understand that actually increasing the model complexity is necessary, you add more units, more layers, etc. I think that's a more principled approach than just having a very, very large neural network and sort of hoping that it's going to converge to a reasonable solution.
Yeah. So, and on generative models, so in your work, apparently you had a paper on training bidirectional GANs with hints. So, and there you introduce auxiliary information to stabilize training. So, given that diffusion models have largely supplanted GANs in generative tasks, do you believe the concept of incorporating hints or side information has broader applicability for stabilizing adversarial or self-supervised learning systems?
Yes, I think that's a very good idea in any type of, I think, learning application. So that's the thing that I've mentioned before. So normally the criterion that we use in training a model is just the data misfit. But if you have some sort of additional auxiliary information or additional constraints that should be satisfied, then you can always include them as additional terms in your error functions. Like a nudge, it's like saying that, well, it's if you have two different solutions have the same error, prefer this one. So there is this additional term or additional constraint that helps the neural network or the learning model converge to a better solution. I think in the case of generative models, it's actually very important because, for example, think about generating images, right? So normally, so think about something like GAN. So your criterion is the error on the discriminative model. But you know that what you're generating are images, and we know that there's a lot of structure in an image. There's a lot of regularity. So any type of additional criterion that you can add to the error function that checks for regularity will be very helpful. So this is regardless of the learning algorithm. So that's the idea, is that if you have any, so if you have any sort of prior information that can help the machine learning model to converge to a better solution, or to be able to say out of two solutions which one is better, then it's always a good idea to add that as an additional term. So the idea is that you have this normal error, and you have something like a lambda times another term, or you can have a lambda times another term, lambda 1, lambda 2, lambda 3, etc. But as I told you before, you should be very careful when you're adding such criteria, or you should be very careful in adjusting their lambdas, because those are your prior beliefs, and they may not always be guaranteed to hold. So that may actually work to disadvantage. But if you have those terms, it's a good idea. and especially in generative models, because as I told you, whatever you're generating is not just an ordinary image. It's not just an ordinary two-dimensional matrix, right? So you're generating an image. And an image has a lot of structure. There's a lot of continuity, so you have all sorts of smoothness. For example, the colors change gradually, the objects change gradually, the contours are smooth, etc. So any type of error term that you can add to your generative model, I think will be very helpful, especially early on when you're converging to a solution.
So this approach of hints is not only applicable to bidirectional GANs, but also to other probably other frameworks, right?
Exactly. Actually, when I mentioned before, so if you think about something like weight decay, L2 regularization, so that's another hint, right? So we know that we know that, for example, we may have a lot of weights that are not necessary. So what you do to the data misfit, you add a penalty term that penalizes the weights if they move away from zero. So what that additional term does is that if a weight is not necessary really to decrease the error, then there's going to be this other term, the nudge term, the hint term, that will move it towards zero. So it's as if that weight wouldn't exist, so there's not going to be overfitting. So it's the same idea.
So these hints are typically used in the loss function, right?
Yes. So you add those as additional terms to your loss functions.
Okay. So in that sense, regularization is also a kind of hint.
Exactly, because regularization corresponds to assuming smoother models. And so what you do is that you add a hint that penalizes unnecessary complexity. So you have this data plus complexity. So when you're minimizing your error, you're trying to get a solution that has small error and is also as simple as possible at the same time. For example, in the case of our paper, so what we did was you want the discriminator error to be small, but what we did was we also added an encoder term, which will be going to be the inverse of the generator. So you generator and encoder together, they work as an autoencoder, right? So what you do is that we also take the output of the encoder and we use it as another criterion. So this was, for example, an indirect way of making sure that the output you're generating looks like an image, right? So because it's comparing with the original image. So that was the idea.
Yeah, let's connect this to representation learning.
Okay.
So your work shows that different covariance matrices lead to more complex decision boundaries.
Mm-hmm.
And shared covariance results in simpler linear boundaries. So the question is, in modern deep learning, do you think representation learning succeeds in part by transforming data into spaces where class covariances become more similar, thereby enabling simple linear classifiers to perform well?
Well, if you think about, if you're talking about deep learning is doing something a little bit different. When we talk about covariance matrices, we're talking about, so that was more like the parametric case when you assumed, for example, the Gaussian distributed classes. Now, if you have Gaussian distributions, so if you have something like a parametric model, as you said, if the covariance matrices are shared, then you get linear boundaries. If the covariance matrices are different, if you're using Bayesian classification, then you get quadratic models. So that's a way of doing model selection. So whether you get the linear boundaries or quadratic boundaries. In the case of neural networks, actually, those things are done a little bit differently. For example, if you think about the different covariance matrices, so it leads to a quadratic boundary. So it corresponds to starting from your original model and doing something like adding like higher order polynomial terms to your inputs, and then doing a linear classification. I don't know if it makes sense. For example, so let's say that you want to do nonlinear regression, right? So let's say that you're doing linear regression. So in linear regression, your formula is y is equal to a plus bx, right? But if your underlying problem is quadratic, there is no way you can fit a plus bx. You need a plus bx plus cx squared, right?
Yes.
So
Yes.
what you can do is that you either learn somehow in your neural network to calculate something like x squared in some hidden layer, in some hidden unit, right? Or what you can do is that you additionally generate a new input, let's call it z, which is set to be equal to x squared, right? And then when you write a plus bx plus cz, that will look like a linear model, but it's actually going to be a quadratic model, right? It's going to be linear in the xz space, but it's going to be quadratic in the x space. Anyway, so it's sort of like a pre-processing of the data. So whenever you're going from shared covariance matrix to different covariance matrices. In the case of neural networks, so actually that corresponds to making your model more complex. It corresponds to being able to extract more complicated features of the input. In the case of deep neural networks, that's done by adding more layers or adding more units. So those are two different ways of making models more complex. Right. So
Yeah.
the deep neural networks are more non-parametric in that sense, that they do not assume that much structure about the probability distribution.
Yeah, I think the question is coming in. I mean, if I interpret it correctly, the question is probably related to this idea in neural ODEs, right? Neural ODEs, neural networks, which solve ordinary differential equations. So there, any curve, any curvature can be represented as a series of small, tiny line segments.
Okay.
So I think that's where this question seems to have the base. So the idea is for any classification, do we can we think that deep learning is coming up with linear surfaces or linear classification areas together, combining which we'll get a more complex decision boundary? I think that's where it's coming from. But I think, yeah, you kind of answered that question. So I just wanted to clarify the background.
Yeah, actually, one way of looking at deep neural networks or multi-layer perceptrons in general is that, for example, let's say you're doing linear regression or linear classification. So normally it's you have your inputs and you have your outputs. So you have one layer, right? So it's a linear model. But if the problem is not linearly solvable, if it's a nonlinear regression or a nonlinear classification problem, you need to process your data. So you need to map your data to a new space. And in that space, the problem should be linear. So this corresponds to the last hidden layer in your deep neural network. So all the layers from the input to the last hidden layer, you can think of as pre-processing your data in such a way that, for example, if you're doing linear classification, in the space defined in the last hidden layer, classes are linearly separable. So that's sort of the one way of looking at things. So you can either do it by defining features yourself, or by assuming representation yourself, or you can have a deep neural network with multiple layers, which incrementally transform your data until it gets to a representation that's abstract enough where the problem is linearly separable. I think this is for example, if you think about something like a Fourier series or Fourier approximation, in that case, your output is written as a weighted sum of sines and cosines. So here, what we're doing is that we're writing the output in terms of the sums of the values in the last hidden units. Again, a weighted sum, right? So it's just, in the case of Fourier, you're just using sines and cosines. In the case of deep neural network, we do not assume sines and cosines. What we assume is this sort of like a general model of this dot products followed by a nonlinearity, which is sort of flexible model. And we assume that the neural network will be able to fill in those weights so that those hidden units will be able to generate a nice enough representation so that we can write the output as their weighted sum. Does it make sense?
Yeah. So yeah, it's a good way to summarize the compositionality of the decision spaces.
Yeah, or for example, if you're doing polynomials, so you have a bx plus cx squared or dx cubed, etc. Now you have a weighted sum of x and x squared, x cubed, etc. So those are, you can also think of them as basis functions. But those are polynomial basis functions. In the case of Fourier, they are sines and cosines. In the case of deep neural networks, these are hidden layers. And one nice thing about deep neural networks is that those hidden units can contain multiple layers themselves. So you do not need to generate features in terms of the original features. So what you do from the original features, you calculate some features, and then from those features, you can calculate more complicated or more abstract features. So you have these layers of these where incrementally you're getting a better and better representation. And once you get to the last hidden layer, when you believe that you have a good enough approximation, you have a good enough basis functions, then you write the output as their weighted sum in the last layer.
Yeah. So there are some compliments to you on the new book on the chat window. And there's also a question.
Yeah.
So the question is, I think this is a trivia question, like what was the inspiration behind your latest book cover? So I think the book covers are decided by the publisher, but I'll let you answer that question.
Yeah, the book cover was the so they asked me what I'd like as a book cover. So I do not like book covers about machine learning that contains, I don't know, graphs or robots or etc. So I wanted something that's as abstract as possible. So I said this to the publisher, and they sent me a set of images, and out of those images, so that was the one that I liked best. So I think that's good, and the colors are nice, and it's abstract enough. So yeah.
Yeah.
And the color sort of matches the color of my earlier books, so that was another criterion.
Yeah. And so switching back to tabular data and decision trees. So your research on omnivariate decision trees allows for different node types at each split. So with the rise of automated machine learning pipelines, do you think adaptive node type selection in decision trees could outperform fixed structure deep networks and tabular data, particularly in settings where interpretability is important?
Yes. So let me just explain very quickly what the omnivariate decision tree was. So normally when we talk about decision trees, so we have univariate nodes. That's to say that at a node, you use one of the attributes, and typically if it's a numeric attribute, you check, for example, whether it's greater than this value or that value. So that's a univariate node. And as you said, these type of trees are very good if you're doing tabular data. That's to say that if you have like these different features and they're sort of independent. But if you have something like, I don't know, if you want to do something like face recognition, such a decision tree is not really useful, because you cannot just look at the individual pixels, and you cannot say that if this pixel has this value and this pixel has this value and this pixel has this value, it's going to be this person or this other person, etc. So even in the case of handwritten digit recognition, you cannot just look at the individual pixels and make a decision. So in that case, you need to look at all the pixels, or a large enough patch of the original input. So that's why, for example, what people do is that they keep the decision tree, but in a decision node, you use a multivariate node. That's to say that you're using all of the features, but instead of using just comparison with a single. So what you do is that you use all of the features in the linear multivariate node, you take a weighted sum, and then you check if that weighted sum is greater than or less than a certain value. So that allows you, for example, to look at multiple pixels at the same time. But it just sort of depends on the application. So what our idea was in the case of omnivariate decision tree is that at any layer, when we're generating the tree, we try both of them. So we try the univariate, we try the linear multivariate, and we also tried the nonlinear multivariate, which was actually a small multilayer perceptron that was generated just for that particular node. And then we choose the one that performs the best. So we found that to be very useful because, again, depending on the application, you may prefer to use this univariate nodes, or you may prefer multivariate nodes. So to say, it allows you to better match your model with the properties of the data. So that's why I think it's very promising. You can also think of the similar things with neural networks. For example, let's say that you have well, typically, for example, you have a fully connected layer, you have a multi-layer perceptron, and all of them, for example, are maybe sigmoid or ReLU. Or you can have, for example, some of them like sigmoid, some of them ReLU, some of them maybe like Gaussian, etc. Right? So that allows you a better, a more flexible model.
Yeah. And coming back to adaptive architectures that we kind of talked earlier. So you explored growing neural networks that expand as learning progresses. So do you believe adaptive model growth could serve as a viable alternative to today's fixed large-scale deep learning models?
Yes, I do. I think that it's a more principled approach because the current approach of, well, let's build a very large neural network and hope that it converges to a good solution is not, I don't think it's principled enough. I think it's better that we start with a small model and then add to it maybe layers or neurons or maybe representations in time when we really need additional complexity. I think it's also efficient in terms of computation and energy. So I think that's the way to go. So yeah. So I think that it can be. I think it can be used in deep neural networks. Very, very, very. So I think that there may be very interesting architectures as a result of that. So really, because the current approach is just you have a lot of weights, you have a lot of neurons, you have a lot of layers, and I just hope that they somehow converge to good values. But we do not really know if they're really necessary. But that's one of the That's one of the points that relates to the earlier question from Daniel. Is that do we really know what a deep neural network is doing? And the answer is no. So we may have a lot of layers, we may have a lot of units. Maybe some of those units, some of their weights are not really doing anything useful. So I think if we go incrementally, we can at each stage make sure that anything that we're adding is helping or not, or we can test whether anything that we're adding is helping or not.
Yeah. And let us talk about kernels. So in your work on multiple kernel learning, you demonstrate how combining kernels enables integration of heterogeneous feature spaces. So given the dominance of deep learning, how do you see the role of kernel-based methods evolving? So do you anticipate hybrid approaches that integrate kernel methods with deep learning or deep neural networks, or will deep learning largely replace them?
That's a very good question, and that's a yeah. So the approach that we worked on was in combining multiple kernels, but we had an approach that sort of looked like the mixture of experts. So normally what you're doing is multiple kernel learning is that you have these different kernels, But actually, kernels corresponds to different representations, right? So, if you remember, every kernel is a dot product of the basis functions, and basis function is a transformation of the input. So each kernel assumes a particular feature representation, which corresponds to assuming a particular type of positioning in the input space or a particular type of distance measure that's applicable to that data. So there's this relationship between features and distances and kernels. So in multiple kernel learning, normally what people did, so this was in early 2000s, was they sort of took a weighted sum of the kernels, but using all of the kernels at the same time, but those weights are learned from the data, but those weights are fixed over all x. So what we did together with my PhD student at that time, Mehmet Gönen, was something like allowing something like a mixture of expert architectures. So in addition to the kernels, we had something like a gating model, which looks at the input and saying that for this type of input, use this kernel. For this other type of input, use this other kernel. So that was the interesting bit about that work. So I think that's a good idea. It's just a generalization or an application of the mixture of experts idea to kernels or to support vector machines or to kernel machines. Now, as for your other question about whether we can integrate kernels with neural networks, I think we can, and that relates to my earlier point about using additional features whenever we can, if we believe that they are useful. So underlying each kernel is a representation, and if we know that that representation is good, so for example, we can give them as another set of inputs, for example, to our deep neural network. So you can also think of these kernels as some sort of a predefined pre-processing stages, for example, before you use a neural network, right? So that's the idea. So if you know that if you have for example, an application where you know that a certain kernel is going to work very well, then you can use that kernel or the basis functions that underlies that kernel as a pre-processing stage. And then the neural network just learns the rest, just like we talked about transfer learning before. Because each kernel learning actually corresponds to an assumption about a certain input representation or a certain distance functions, etc. But you need to be very careful because whenever you're doing this, you're doing a pre-processing. And if you're not sure about the correctness of that pre-processing, it may actually work to your disadvantage. So it's a little bit risky. So any type of change in this network structure representation or error function, etc. So that may help to the learning process or that may hinder the learning process because it may also imply imposing your prior assumptions about the application. So if your assumptions are good, they're going to be helpful. If your assumptions are bad, they may actually be bad. So they may actually make the accuracy worse.
Yeah, I think Daniel has a question, follow-up question. Daniel?
Yes, Professor Alpaydin, I put a message in the chat about something orthogonal to our current AI implementations, especially with deep learning. This is the fruit fly connectome, and it achieves tremendous capability from an extremely tiny number of neurons. And this appears to me something we are completely not using in our current AI systems, especially as we move to robotics. Can you guesstimate maybe what it will take to bridge the gap between these two completely different paradigms for AI?
Yes. Well, that's a very good point. I think, but I sort of don't like these phrases like, but in the engineering context. So when we talk about intelligence, or when we talk about things like neurons, or when we talk about learning, we need to be very careful because we do not actually know what happens in nature. So what we consider as neurons in engineering or in our deep neural networks, for example, are probably very, very simplified versions of what actually happens in natural neurons. So it may be the case, for example, that a neuron in the human brain may correspond, I don't know, to something like maybe multiple layers in our current architectures. So there doesn't need to be a sort of like a one-to-one correspondence between the interpretations of these concepts in nature and their interpretations in the engineering context. So for example, I don't like the name artificial intelligence, or I don't like actually calling these artificial neural networks because we do not really know what natural intelligence is. We do not really know what natural neurons do. So so your point is very good that it has a small number of neurons and a relatively small number of synapses, and that's doing very, very complicated things, wonderful things, whereas it looks like we're needing, like, I don't know, maybe millions of neurons, billions of weights, etc., for relatively simpler applications. It's just because that our neurons are their neurons, or artificial neurons and natural neurons are probably not the same. And actually, they do not need to be the same either. I think that you see my favorite example, of course, it's not my example, is, for example, when you think about flying. Now, so you have birds that fly, and we also have airplanes that fly, but they do not fly in the same way. While they both have wings, and they both need to obey the rules of aerodynamics, the underlying physical rules. But for example, an airplane, when it flies, it uses jet engines. It doesn't flap its wings. So although both of them have wings, if you like, they're not using wings in the same way, or they're not. So they both need propulsion, but they generate the propulsion in different ways. So in nature, birds flap their wings. When we build airplanes, we have propellers, or we have jet engines. So there doesn't need. So my point is that doesn't need to be a one-to-one correspondence. So you cannot say that, for example, I don't know, a seagull is flying so wonderfully, and why an Airbus cannot fly like this, because they're sort of like two different systems built for two different solutions, etc., for two different applications. For example, we're interested in building very large airplanes because we're interested in carrying people and also cargo. So,
But I guess just to more focus is that what I find intriguing is that, especially in your bird versus plane example, yes, they have several differences, but more importantly, they have an incredible similarity in the following way: in the shape, the form of their design. In other words, they both have wings, they both have tail feathers, they both have like aerodynamic shape. These are form characteristics. And what I find intriguing is that the connectome model produces these emergent behaviors, I suspect, from the form of the network of the connectome. And I think there is a rich field to mine in the form of the connections between what we consider our abstract neurons.
Yes, yes, I agree. But I want to raise another point. Is that so? The solution found by nature and the solution found by engineers are solutions for two different applications, for two different needs, and using two different types of materials, if you like. They both need to obey the rules of aerodynamics because they both need to fly. But for example, we can build airplanes that are much larger than birds. They can carry much larger load. They can carry people, whereas birds cannot. And they can also fly much faster. So it's a good idea that we sort of take inspirations from the nature, but we do not need to be constrained by the solutions found by nature. We can get better solutions because
Yes,
we
I
have
agree with
better
you.
because we have better. I don't know. We can go beyond. For example, there is no reason to assume that human intelligence is the highest form of intelligence that's possible. So we are intelligent. So we have a certain level of intelligence because that was the level of intelligence needed for us to survive in certain particular configurations during the evolution in the past, right? So we could have evolved to be a little bit more intelligent, or we could have evolved to be a little bit less intelligent, depending on the circumstances that we've encountered in the last, I don't know, millions of years, right? So the idea actually in engineering is we're sort of more ambitious. So we want to get a definition of intelligence, or we want to be able to get find ways of achieving intelligence so that we can go beyond human intelligence. So that's why, for example, we're interested in deep neural networks, and I think that's a very critical, very critical point now. Is that now, for example, we have these large language models like ChatGPT, and now the question is, well, how they can scale, or can they scale? For example, if we make those networks 10 times larger, can we achieve 10 times more intelligence? Or if we make them 50 times larger, 100 times larger? So I think that's the critical point. Or is there any sort of inherent limitation due to the fact that we have these deep neural networks? So it may be the case that that may be, for example, the highest form of intelligence that you can achieve by networks of processing units. I don't think there is, but we may be needing a different type of neural network architecture, or a different type of neurons, or a different type of connectivity to be able to maybe to get to the next level, right? So this is related to your earlier question.
Thank you.
Okay.
Yeah, while we were talking about all this, I became curious to know your opinion about the promise of reinforcement learning. There are some contradictory views about reinforcement learning from many experts. So I was wondering if you have any opinion on the future of reinforcement learning.
Well, I think that all learning algorithms have their place and have their purpose. Supervised learning is very nice, but it's very difficult to find good labels, because you need to have a supervisor who should be able to provide the desired output for a large set of inputs, and that's very costly to achieve, and sometimes it may not even be possible. For example, if you're learning how to play chess, there's no such thing as the best move at a current point, so you need reinforcement learning. So hope, but of course, it would be best if we could solve all problems using supervised learning, because that's the case where we get maximum feedback from the environment. That's when we have maximum information. So it's sort of the easiest case. But if we do not have that, well, we can have some sort of limited feedback. For example, in game playing, we do not know what's the best move for any position, but we can understand at the end of the game whether we win or lose. So that's a very limited feedback, but that's better than nothing. That's better than unsupervised learning, where there is no feedback at all. So depending on how much feedback you get from the environment, you can use supervised learning, you can use reinforcement learning, and you can use unsupervised learning. I think they all have their uses.
Yeah, the reason I asked is because reinforcement learning is more like trial and error, and that also without any, like for instance, the simulations that we are doing, they are requiring like even after 50 million iterations, episodes, we are hardly able to get like 4% accuracy.
Yes,
Yeah.
I think what helps in those type of scenarios, I think it would be a good idea to try something like curriculum learning. So instead of learning with the original problem, think about a simpler case, a simpler version of your original task, right? So where you have less flexibility, a simpler environment, a smaller set of actions, maybe shorter rewards, etc., shorter sequences until you get to the reward. And then incrementally make the world a little bit more and more complex, right? So it's like when we're growing up. So when we're babies, there were a small number of tasks that we need to do. And in time, we need to learn more and more. So I think that's that may be more or less that may be a good strategy. So try with a simple world, try with a simple environment with a small set of actions, and then incrementally make the model more complex.
Yeah, yeah.
That may be helpful, yeah. I don't know your particular application, but I think curriculum learning is a very good idea, and it's also what we do in natural learning, right? So you go to the primary school, and then you go to the secondary school, then you go to the high school. So you start with learning the basic concepts, and then you building on them, you learn more complicated concepts, etc.
Yeah,
I think curriculum learning is a very, very good idea in general. Yeah.
Yeah, that's catching up. Yes, I agree. Yeah. And you talked about bias variance trade-off. So my students were kind of wondering how you interpret the relevance of this trade-off between bias and variance in the context of these modern deep neural networks, which are over-parameterized, like trillions of parameters and all. In spite of the complexity and over-parameterization, they are able to generalize well, despite their size. So what is your take on that?
Well, my take on that is that so these are there's no memorization. So if you have a very complex model, so let's say that you have an unnecessarily complex model, but if you have a lot of data, then you can constrain that model so it doesn't overfit. So for example, let's say that you use something like a third degree polynomial, and then your data is sampled from a linear model. But if you have a lot of data, you can constrain the third degree polynomial so that it works like a linear model. If you have enough data, of course, only in the domain where you provide the data. Out of the data, it's going to extrapolate very, very badly outside of your domain if you use a high degree polynomial. But if you're talking about limited domain, if you provide a lot of data over there, then it's going to learn to behave linearly in that region. So that may be one explanation, is that we have very large neural networks, maybe unnecessarily large neural networks, but we also have very, very large data sets, so they do not memorize. Or even if they do memorize, they're memorizing something good. So that's it's not overfitting. Another reason is that whenever we have large neural networks, people also typically use some regularization methods, right? So they use something like maybe L2 regularization, or they use something like a dropout, or if you have like convolutional neural networks, because of weight sharing, you're using small number of parameters, etc. So there may be some additional type of constraints that allow them not to memorize. And it may just be the case that I think that's, it's probably my intuition is that there's a lot of weights that are not really necessary, but there are also these other weights that are not necessary, but they sort of cancel each other so that they do not lead to any problem. So that's sort of my understanding of the thing. So there are these weights, but they are not really harmful because they are sort of like compensated by these other weights. So they do not need to lead to any problems.
Yeah. So we are over the time, but is it okay if we go a little over?
Sure, go ahead.
some
Yeah.
time? Okay, thanks. Because I know it's late for you in Turkey. So on distribution shift, so in your book Machine Learning from 2021, you discuss how many models assume stable data distributions between training and deployment. So, but in practice, data distributions often shift. So what strategies do you consider most promising for detecting and adapting to distribution shifts without requiring continual retraining from scratch?
Well, that's a very good question. That's a very deep question. But I'm not really familiar with this covariate shift problem. I know that it's a real problem, especially in financial domain, for example. Suddenly things may become very, very different very suddenly. So all these systems should be able to adapt themselves. I do not have any like immediate algorithm or technique that I can tell you. I know that it's a real problem, and that, but probably, I don't know. What I would do is, but yeah, I think your approach makes sense. Is that first you need to be able to detect it. So you need to be able to detect that now your input is coming from a different distribution. So so that may be done maybe in an unsupervised manner. But then correcting it probably requires something like a supervised stage. I don't know. I need to think about it.
Okay, that's fine. Let us explore delayed feedback settings. So in domains such as agriculture or climate monitoring, data is collected continuously, but ground truth outcomes may only become available after significant delays. So how can models be effectively trained in such delayed feedback settings while still enabling early detection of issues?
Well, yeah, that's another. So you're saying that the input is changing, but we do not know what the correct output is until a certain delay, right?
Exactly. Yes.
Yeah. Well, that's interesting. I think it's related to the question before, right? So there's something like a covariate shift. I don't know. I think it depends on the. I think it probably yeah. I would probably use something like an unsupervised learning application to be able to first understand that there's a change, and then. But if it sort of looks like the change, so if that type of change is appearing frequently, in more or less a similar way, then there may be a way to also predict the effect of the next change. So maybe something like a sequential model may be used. I don't know. It depends on the application, I think. Do you have
Yeah.
any application in mind or any?
So the application that my students had in mind was agriculture and climate monitoring. Like
Like if the climate is changing, what's going to be its effect on the output or something like this?
yeah. So the data is changing continuously, right?
Yeah.
But the real, I think this, as I think about it, this may be a good problem domain for reinforcement learning, where reward distribution plays a role. Right?
Yes, or if it's like if the change, because we're talking about a change in time, this may be a good application also for some sort of a sequence. So you may think of this something like a sequential learning, or maybe something like a, I don't know, outlier detection in the temporal domain. Because if things are changing differently than it changed before, it's like an outlier in the temporal domain, right?
Yeah.
So you may be, so you may think something like maybe like an LSTM, or maybe something like a transformer, because you may want to focus on certain different aspects of the temporal sequence, etc. It's an interesting application, yeah. And also you may use, for example, something like a reinforcement learning, because if you may just maybe know that it's getting better or worse, you may not maybe knowing exactly what the output should be. So then it will be a case for reinforcement learning, yes.
Okay. And one of our favorite topics is support vector machines and kernel methods. So in your 2011 work on multiple kernel learning, you explored both linear and nonlinear kernel combinations. So given recent developments such as automated kernel selection and deep kernel learning, do you think revisiting this work today would lead to a different outcome?
Okay. But it just corresponds to different ways of combining models. And then, for example, we can think about linearly combining neural networks or non-linearly combining neural networks. So it's so whether it's the support vector machine or not is, so you can think of actually each hidden layer as doing something like learning a kernel, right? So if you look from that perspective, whether you're combining kernels or you're combining layers, or if you're combining networks, is not really much different. For example, the approach that we talked about when we had this multiple kernel learning is it looked like mixture of experts. And mixture of experts, I think, is also a very good idea in all sorts of applications. So when you're combining these multiple models, you can be combining kernels or you can be combining deep neural networks. I think it makes a lot of sense in many applications because, but instead of maybe, so if you, let's say that you have a problem that you're trying to solve, and it naturally, you may see that actually that typically big problem, you may decompose it into, for example, 4 different problems. Okay, so instead of trying to train one big neural network on all these problems at the same time, a better strategy may be to, if there is such a natural decomposition of the tasks, is that you train 4 different neural networks for these 4 different tasks. And then whenever somebody asks you a question, for example, let's say that you can build a large language model like this, right? So because when you ask to a large language model, depending on the prompt, for example, somebody may be interested in getting an answer to, I don't know, a political question, or they may be interested in writing code, or they may be interested in generating an image, or etc. Right? So you can think about actually different type of tasks that you would expect from a large language model. So instead of training one very, very large neural network to handle all the tasks, so what you can do is that you can have a system that looks at the prompt, and then by looking at the prompt, choosing one of these smaller models and using only that. So that will be very efficient because first you can train these models separately. And also whenever you're doing a calculation, you're using a relatively simpler model. So that's going to need less computation, less energy, etc. So I think from that point of view, so the whether linear, nonlinear, local, global, etc., actually making such a distinction will probably be very useful. So I don't know whether the large language models that we use nowadays are built using this mixture of experts approach. But I think that it's very promising because the advantage is that you can also train them independently. So some of these tasks may be, for example, changing very quickly. So you need to train them maybe very frequently. But some of these tasks, for example, may be not changing. So you do not maybe need to train them very frequently. So it's also allows you to decouple the trainings of these models. So I think that mixture of expert approach is very, very promising in real life.
Yeah. Yeah, and it's already being used in large language models like DeepSeek, I believe. So
I think, yeah, that makes sense.
yeah. So Daniel has a question. How can we design models that learn continuously without separate training and inference phases?
Yeah, that's a very good question. So there is this difference between training and test, or difference between training and inference. In the case of training, there is a feedback mechanism. So in the case of supervised learning, the feedback is very explicit. So somebody tells you, you generate this output, but this should have been the correct output. Or in reinforcement learning, you generate an output, and once in a while, the critic says you're right or you're wrong. But when it says you're wrong, it doesn't tell you what the right output is. It just tells you you've done something bad. So training requires this type of feedback in terms of you keep on using models, and while at the same time you're also generating feedback from the environment, and then you update yourself slowly. So you can do this, and it will be very interesting, but the requirement is that during the inference phase, you should also have a mechanism of receiving some sort of feedback from the environment about how good your actions are.
Yeah. And on visual data, right? So in your work on visual pattern recognition, you explored downsampling images to reduce computational cost. So if higher resolution inputs and larger observation spaces are used instead, do you expect this to increase the risk of overfitting, or is there an optimal balance that modern datasets can support?
Right. Okay. Well, actually downsampling, so you can think of downsampling as a convolutional layer where the weights are fixed, right? So downsampling, you're just taking an average, right? So you're taking a local average. So it's a convolutional operation, but it doesn't have any trained parameters. So ideally, if you have large resolution images, instead of downsampling, you can have a convolutional layer there with trainable parameters, and that's going to work better than downsampling, because downsampling may not be the ideal way of compressing that information, right? In a convolutional layer, generally what we're doing is that when we go from one layer to another one, resolution is decreasing while we're increasing the number of filters, right? So downsampling is something like a fixed convolutional layer. So if you're sure that in that downsampling operation, you're not losing any information, then that will be nice. But if you have large enough data, I think a better way is get rid of downsampling, introduce another convolutional layer, and also train those parameters. And then if you have multiple filters, you can have multiple ways of generating the next resolution. So not just downsampling, but you can think about other. So it depends on the data. So if you do not have very large data sets, use downsampling, but it corresponds to, again, smoothing the data. If you have large enough data, it's better to introduce a convolutional layer and also train the parameters of that layer. So you see, there's no magical answer in this case. It also always depends on the data, because you're increasing the complexity of the model. So it's just, your question is very correct, is that you're increasing the complexity of the model. If you're instead of downsampling, you use the original data. So you need to make sure that you have enough data to constrain that extra variability so that it doesn't lead to memorization.
Yeah.
So it's again the bias-variance dilemma, right? Because if instead of downsampling, you're introducing there a trainable layer, you're increasing the complexity of your model. So there's a higher risk of overfitting. You're increasing the variance.
Yeah. So let us switch gears a little bit and talk about interpretability and sort of segue into social concerns, right? So many machine learning models achieve higher accuracy at the cost of interpretability. And so based on your research, do you think interpretability methods such as decision path analysis can ultimately contribute to improved generalization rather than merely explaining model predictions post hoc?
Wow, yeah, that's a okay. Now that's another thing that we need to be very careful. So it sort of relates to our previous discussion about prior assumptions, because what we consider, well, when we say something is interpretable, we're saying that it matches to our maybe subjective criteria of regularity. So that's what we consider interpretable, right? So we have a certain way of looking at things or explaining things in our mind, and that may be subjective. And we're checking if the model learned from the data matches to our expectations, right? So that's what we consider interpretable. So in that case, we need to be very careful because interpretability is basically a subjective criterion, or because it's something like a priori criterion, our interpretable criterion may not be the best one that matches to that application. So if we sort of enforce interpretability, we may be imposing our subjective beliefs on the models, which may be harmful. So any concern about interpretability should have lower priority. So our highest priority should be how well we do on test data, assuming that we have large enough training data and we have large enough test data. Interpretability is good, but it may not always be necessary because we may not have the right criteria to define what interpretability is for that application, right? For example, previously I talked about Kepler, Newton, etc. So Kepler came up with a model, but at that time it wasn't interpretable. So it just came up with elliptical orbits, etc., or varying speeds, and nobody knew what that meant. But when Newton came up with the theory of gravity and laws of attraction, etc., then suddenly whatever Kepler found has become interpretable, right? So that's why this interpretability is, so if it's interpretable, it's nice, okay? But I do not favor constraining models so that they learn interpretable solutions. I think the model should be free to do whatever the data requires.
Yeah.
I don't know if that answers your question, but that's my belief. So interpretability shouldn't be something like a very strong constraint that we impose on the application. Or you need to be very, very certain that whatever your interpretability measure is, it really applies to that application. Otherwise, it may really make things very, very bad.
Yeah, that's a useful perspective, I think, because yeah. The next question is probably on the top of minds of many people. So you also discuss the societal impact and value of data and machine learning. So do you believe individuals should be compensated for their contributions to training data? And if so, how might such a system be implemented in practice?
I think there are already people who earn money by labeling data, right? So that's how these large language models are trained, right? So it's already something like a job. People look at data and they label them, right? Like Amazon Turk.
Yeah, that's right. But I think
Right?
what we have
So
in
maybe
mind,
you're talking about the ordinary people who just
right,
provide data without actually knowing that they're providing data, right?
yeah, exactly.
Yeah. So I don't know. It's sort of tricky. I mean, you can say that, well, you're indirectly being compensated. For example, let's say that you're buying grocery from a supermarket, and that supermarket uses your data to predict what you're going to buy, right? And if that predictions are useful, then you're going to be more certain that whatever you're looking for maybe next week is going to be available for your purchase, right? So whatever data analysis that's done by supermarket is also indirectly working to your advantage. So you can say that you're sort of like already being compensated, right? For example, in the medical domain, they use your data, but they may use that data to find a cure for a disease. And that cure for that disease, of course, the company will also earn money because they're producing drugs, but it will also be beneficial to humanity. So data collection is not necessarily always a bad thing, and it's not always a sneaky thing, or shouldn't always be, I don't know, avoided. But there's another perspective. Let me ask you something like this. Let's say that you collected the data for some application, right? And you sold that data to me. And I used your data to build a model, and that model failed, right? Will you be responsible from the bad outcome because you've generated the data?
Well,
right? So it goes both ways. So these things should be really. So I think lawyers are really thinking about these things. So it's because in machine learning, it's not just an engineering problem. There's an engineering problem, but there's also the data, and the quality of any solution always depends on the quality of the data. So if you're providing your data somewhere, then you should also be, maybe you may be compensated because you can sell that data, but you should also at the same time accept the responsibility that your data may lead to wrong solutions or wrong systems. So that's so it's like a two-way street.
Yeah, that is in fact one of the primary concerns, right? We provide the data and we don't know how the data is going to be used. And what if the outcome is not favorable? And what is the outcome? The grocery store example you gave is fine. I'll be benefited most likely. But what if the data is used for adversarial purposes, like which are not very comfortable to me?
Yes. Yes, I think I don't know. Probably, yeah, you should have some way of, so, yeah, whenever I think that, yeah, to any institution that has some sort of data about you, I think you should be able to say whether you allow them to store your data, to share your data, or use only these type of applications, etc. So it should be, yeah, I think there should be mechanisms for that. Yeah.
Yeah.
Yes.
So along those lines, so your work on active learning focuses on selecting the most informative examples, right? So in contemporary contexts where data collection raises concerns about privacy, consent, and responsibility, like we talked, would you still prioritize informativeness alone, or would you incorporate these human and societal costs directly into the learning objective?
Well, active learning is, but the way I understand active learning is a selection of instances from a large enough data set. So your data set is already large. And then you're saying that, well, there are these instances that are really informative for me. And these other instances are not really. For example, let's say you're doing classification, right? So you have these instances and you have a rough idea where the boundary is. And you want to get a very good idea about where the boundary should be. So then the idea is that, well, can you generate new instances or look at those instances that are closer to your estimated boundary, because those are going to be the real informative instances, right? So in real life, okay, well, I don't know. It sort of depends on the application. I need to think. Do you have any application in mind?
Not exactly, but the idea I think is basically we are trying to leverage the importance of data. I mean, we are trying to get as much context as possible for active learning to happen. So yeah, so there is a cost to that. That's what the question seems to indicate. And do we live with that cost, or yeah, it ties back to the previous question as well. Like, how do we deal with the value of the data? And it's like that.
Yeah, it corresponds to sort of saying that, well, you're generating sort of dynamically an instance, and you're asking the supervisor to label that instance. So what if you saw an input like this? What would be your output? What would be the desired output in that case? Yeah, it's sort of like an active sampling. So because normally in machine learning, we assume that we get the training data. So the sampling is, we're passive in the sampling phase. But in active learning, we're going and we're sampling the data ourselves. But if there was an image like this, what would be its class, right? So in that case, it's very informative, but it requires the intervention of a supervisor. So for example, let's say you're doing classification and you have a difficulty separating ones from sevens. So what you can do is that you can generate an image that looks half like a 1, half like a 7, etc. And you ask the supervisor, would you call this a 1 or a 7? Right? Because depending on the label, then you can move the boundary to the right or to the left. So that's sort of the idea in active learning. But in real life, in different applications, I don't know if we can always generate those instances. And as you mentioned, what would be its cost or informativeness, etc. Yeah, these are all interesting questions.
Yeah, and so you also did research on soft decision trees, right? So in this case, the instances follow probabilistic paths rather than the discrete branches.
Yes.
And this will obviously reduce interpretability, which is a very strong point of decision trees. So do you consider this loss of interpretability an unavoidable consequence of enabling gradient-based training? And additionally, is there a practical approach to converting soft trees into hard interpretable structures for deployment in high-stakes applications?
Yes, that's a very good point. Is that what you can do? Well, we thought about this, but I think we never did any actual experimentation. Is that so? When you have the soft decision tree, of course, instead of hard thresholding, because it's soft, it's differentiable, so you can take derivatives. It's actually a multi-layer version of mixture of experts, right? So it's actually the originator of this idea is Mike Jordan. He's called it a hierarchical mixture of experts. So it corresponds to a soft decision tree. So the advantage is because everything is soft, it's differentiable. But what you can do is that you can, for example, after training or maybe during training or maybe as a different phase, you can maybe softly harden the sigmoids. So you're using a sigmoid because it's soft, because you're taking a weighted sum of the two children, right? In a normal decision tree, in a node, you either take this branch or take this branch. So you have two children, you either choose left or right. So in the soft decision tree, what you're doing is that you're taking a weighted sum. But what you can do is that you can impose, maybe after some learning, these weights to go to 0 or 1, right? So slightly harden them so that it slightly converges to a hard decision tree. Does it make sense?
Yeah.
So that may be possible. And of course, there are two advantages. One is, as you mentioned, it's interpretability, because you have only one path that you're following. So that's good. And another advantage, of course, is efficiency. And nowadays, this energy efficiency is becoming a very, very important problem, because you have only one path. You're doing the calculations on only one path. So you're not doing all the calculations on all the nodes in the tree, as you would have if you had a soft decision tree. So it's also energy efficient. So I think that's an interesting idea. Maybe somebody will try that one day. Is that you start from a soft decision tree where everything is very soft, and as learning proceeds, you slightly harden them. So you start, and at the end, it's really like converges to a hard decision tree.
Yeah.
Right.
Yes.
Because in this sigmoid, you have an addition. You can define a hyperparameter, which defines the slope of the sigmoid, and like so you can slightly move the value of that parameter so that it becomes harder and harder. For example, in time, as you do more and more epochs, you can slightly harden the threshold. So harden the sigmoid so it looks more and more like a hard threshold.
Yeah. So that leads us to the last question I have, and which is on sustainability. Um, so as machine learning increasingly relies on large energy intensive models, how can the field balance performance improvements with sustainability concerns? So do you foresee renewed interest in more computationally efficient approaches?
Yes, I think that's becoming a very, very important criterion because I don't know. In the past, people were always in favor of using computers. I remember in 1990s, maybe even 1980s, people say that, but go green, use computers because instead of doing everything in paper, if you use computers, there's not going to be paper wasted. There's going to be, it's green because we do not, I don't know, cut trees, etc. But nowadays, because of computation, we're using so much power that we need to start thinking about more efficient computing architectures because now everything are computers. Like we have computers, we also have, I don't know, smartphones, which are also computers. So we use computers everywhere. So we really need to think about efficient architectures in terms of energy. So people are very eager to find ways of generating more and more energy. So that's one way. For example, people are getting more and more interested in using nuclear energy. So that's fine. But there should be in parallel a search for finding more energy efficient architectures. So I think that's a very interesting question because, but what I believe, for example, if you think about large language models, when you have billions of parameters, if you have billions of parameters, this means that you're doing billions of calculations, right? If you have billions of weights, you're having billions of multiplications, right?
Yeah. Yes.
So I have a gut feeling that we can use much less precision. For example, you do not probably need 32-bit floating points for all the weights in a neural network, right? Especially maybe in convolution layers. So I think that people are already working on that, but you can, for example, think about architectures with a small number of bits, right? So they're going to be very energy efficient. So can you use, for example, 4-bit weights? Or what do you lose if you use 4-bit weights, etc. So using fixed point architecture, etc. So those are the sort of, I think, directions that people will probably be more and more interested in the future, especially with these AI models, which are really very, very computationally heavy. These concerns are becoming more and more relevant. And it's just an orthogonal direction to all our discussion up until this point. So we need more energy efficient computers, not only for AIs, not only for deep learning, but for everything. So we're a little bit. So you remember. So if you think about, for example, cars, the cars that people built in 1940s, 1950s, they had very large engines because the oil was very cheap at that point. And people were really very concerned about the environmental effects. But in time, we have started working on more and more efficient car engines, and now we need to start thinking about more and more efficient computers.
Yeah, so that's quite insightful. So now we can probably take any questions from the audience. Does anyone have any questions? Please feel free to unmute and ask. So there's one question on the chat window. Sorry, go ahead.
Yes. So this is Armin. Back to the question I asked originally, let's assume, I know some of basic math, and I also do a lot of learning on Coursera, and I did all these things. But what I'm finding is the subject matter is changing so quickly. So what are your techniques for reinforcement of learning of data science? how do you do that? I mean, I know part of it is the experimentation, you know. If I'm like, we went to school, but actually you learn more when you're working, you know. You reinforce what you learned, right? So what do you find yourself as a way to maintain? You actually answered part of it. You said use math. If you know the math, you remember the math, you can apply it in different scenarios. What are other things I can do?
Well, I would recommend that we talked about curriculum learning. I think that's a very good idea, is that you start from the, so if you're interested in learning about deep learning, I would recommend that you start with simple models, simple applications, simple data sets, and then incrementally increase the complexity. So don't just directly try to learn about, I don't know, large language models, which are very complex with their transformers, etc. But try with simpler neural networks. Actually, if you think about the one-layer neural network, a one-layer neural network is just doing linear regression. So it's nothing but linear regression. And if you think about the multi-layer perceptron, it's a non-linear regression. So it's a slightly different version of linear regression. If you think about the logistic, so one-layer classifier is logistic regression. Again, it's a very simple extension of the basic linear regression. So actually, if you think about the theory, if you look about the math, it's also very useful because you understand that actually there is nothing that's really, really very different or very magical or, I don't know, different thing about these things that we call deep neural networks. So that's one of the advantages of knowing math, is that you can really understand that actually it's not really a very big deal. So it's not like somebody suddenly came up with something that's so different from all that we've worked on in the past hundreds of years and came up with a real new algorithm, etc. So these are all things that are incrementally built on earlier models. For example, recently, well, not recently, but people have found out that the attention architecture that people use in transformers is just a different version of the Hopfield model, Hopfield neural network model that was proposed in 1980s, right? So actually, Hopfield got a Nobel Prize for that. So actually, there are these things that are not really that much difficult, and they really depend on our classical knowledge on linear algebra, calculus, differentiability, gradients, probabilities, statistical models, etc. So that's why I think learning mathematics is very important, because you really see then that actually what is new and what is just the same stuff. So, and then once you have those learning mathematical background, then you can start applying them on real data. And as you said, it's very important that you also make experiments on real data, because that's another thing, is that whenever you're doing an experimentation, whenever you have an application in mind, you immediately get an understanding that what you know or what you've learned is useful for something. So you have, I don't know, a better reason to learn more, because you see that what you learn is actually being useful for something. Okay, so that's one of the problems, for example, in undergraduate curriculum, is that people come from high school, we give them courses on calculus, linear algebra, etc. But at that time, they may not be really seeing what those things are going to be useful for. But when, for example, later on you become an engineer, and when you see those things actually being used in real life, in practice, you see that they're actually useful for something. So that motivates you to learn more. So that was this like double-faced stuff that I've talked before. So there should be a process of learning more, having a better theoretical understanding, and at the same time trying more to see what works, what doesn't work, and based on the feedback that you get from the data, you go and try to learn more, etc. So it should be like this parallel process of improving your theoretical knowledge and also improving your, I don't know, as engineering practice. So that's what I would recommend. So learn maths and also start from simple experiments and incrementally make your applications a little bit more complex, until you get to the large language models. Because if you do not know anything about machine learning, or if you have any very limited knowledge, it would be very difficult for you to understand how a large language model works, for example. It's using many different components, and it has many different training phases. There's a supervised layer, there's reinforcement learning used, etc. So it would be very complicated. So start from the simpler things, start from the basics, and attempt things that are incrementally more and more complex.
Thank you very much.
Sure.
So there's one question I think it's worth answering on the chat window. Omar Kilic is asking, what should the role of NGOs be in AI world? So non-governmental organizations, I think that's what he means.
Well, there are many aspects of artificial intelligence that may be in the domain of these NGOs. For example, one of these, but there are different aspects. For example, one aspect is sustainability, the point that you raised. How can we think about, so how can we have, or how can we enforce or maybe nudge the AI companies so that they care about sustainability more? So that's one aspect. Another aspect is the ethical and legal applications or implications of artificial intelligence. So the question that you raised about, for example, can we sell data, or are we going to be responsible from data, etc. So there are all these aspects where AI or machine learning touches the real world, and in all those aspects, I think there needs to be more work done to make sure that these new technologies will actually be useful to humanity, and that they will not going to be harmful. Or another concern, maybe just the point that you raised, is that how can we make sure that AI is not used for bad purposes or malicious purposes? Can we put, I don't know, some sort of guardrails in AI? So these are all very important concerns that people need to think about, which are going to, I think, just going to come in time. It's because this is just it's a very new technology. It's very difficult to see at this point where it's going to evolve. So because of that, it may also be harmful to put very, I don't know, very strict constraints or very strict rules this much early on. Because if you say at this point that this is bad, this is bad, this is bad, and don't do that, that may be harmful, because it may hamper the development of these ideas and new technologies. So I think they should also go hand in hand. There should be a development, so there should be some sort of freedom, of course not complete freedom, but some sort of partial freedom in developing, so that to make sure that we're not actually I don't know, harming the development of ideas. So it's sort of interesting in that. So there should be some sort of constraint, there should be some sort of control, but there shouldn't be too much constraint and too much control, because otherwise you risk, I don't know, destroying a technology that may be very useful in the long run.
Yes. So that's all the questions we have. I sincerely want to thank you for your time.
Well,
and
thank you.
this is a small token of our appreciation for really taking time and giving all the great insights that you shared with us today.
Okay. Well, thank you for having me, and thank you everyone for listening.
Yeah. There are a lot of thank yous on the chat window as well. And then compliments. Very useful discussion. So thanks everyone, and thank you, Professor Alpaydin. So I'll send this certificate over by email as well, and we'll keep in touch.
Great. Okay, thank you.
Thanks. Okay, I'm ending the meeting now. Thank you all.